welcome to a tutorial on the digital number systems. Okay, well, electronics have basically changed the world to a very large extent. All right, and nowadays possibly every type of machine we see around ourselves, okay, be it in the industrial sector, okay, or in our homes, okay, so be it industrial or domestic, whatever it is, we see a lot of these machines, well, they are electronic in nature. So if this box over here basically represents an electronic machine, then well, we know that with all electronic machines, basically there is some sort of command or intelligence associated. All right, so any machine, if you just scale down machines to the very base level, so be it electronic or mechanical, whatever, so any kind of electronic machine, let's just take the example of electronic machine since it's a part of the electronics tutorial. So any electronic machine would basically require what we call an input. Okay, and depending upon the input condition, it will basically deliver an output. Okay, now this output could be used to drive other machines, okay, and control several other devices, or this output could be any kind of result of a calculation that we basically require for our purpose of any kind, or this can be some kind of control signal. So this output can either be control signals, okay, there you go, or this can be some result, okay, some result of calculations. Now, whatever it is, at the end of the the entire operation, I mean, the input and the outputs are basically nothing but data. The input is also a data, okay, and the output is a data as well. So now there is basically a difference in how we look at a data and how a machine looks at a data. So if we're talking about the humans, okay, the humans basically, well, they treat data as they can treat data as well numbers, okay, or they can treat data as well alphabets or whatever it is. They just the data in terms of whenever we just talk about humans, data over here either stands for some kind of values or some sort of symbols, okay, that has certain meanings. Okay, so this is data talking from the human point of view. So this is humans data. And now whenever we talk about machines, on the other hand, they just understand basically one thing. So data in terms of machines. So if I just talk about machine data, the data in terms of machine language, they just mean only one thing. That is binary signals. Okay, binary signals. There you go. Now binary signals are basically consist of either a logic 1 or a logic 0. So here a logic 1 physically means that a circuit or some sort of a connection is in the on state, okay, and a logic 0 signal on the other hand means that the circuit or something is in an off state. So a machine basically understands nothing more than ones and zeros, and this was basically the need why we needed to have a binary number system. Okay, so the binary number system basically paved the way for creating intelligent machines such as electronic devices and processors, and all the intelligent electronic control stuff that you see around nowadays are all based on the binary number systems. But when we human beings, whenever we go to interact with the machines, well, we don't do so well in understanding the binary signals, continuous streams of ones and zeros, and they just seem to confuse us. So this is very confusing whenever we just look at it from our point of view. That's a human point of view. It just appears very confusing. So what we do is that, well, we just would like to represent this entire chains of ones and zeros into something more meaningful that we understand. Well, we understand numbers, right? And numbers consists of certain symbols. So due to this problem over here, so what we basically did was that we just converted the digital number systems. Okay, so if this is the digital systems, or rather we just included in digital electronics a part that we call digital number systems, or more so if I would generalize that, digital data. So we tried defining digital data in terms of two most important types of data types. Okay, so one of them was the octal number system, and the other was the hexadecimal number system. So these are nowadays the most important two types of digital number systems that are currently in use. But the most important of them, I mean of the two over here, being the hexadecimal, is very important whenever we talk about certain digital systems that employ processors. I'll come to it in a little while. Now, if I just give you the charts of the octal and the hexadecimal number system, but before that, let me tell you, now they were just created from the binary numbers. Okay, so it's just a shorter way. Both the octal and the hexadecimal number systems are just a shorter and more meaningful way in terms of human beings of representing binary numbers. So both octal and hexadecimal numbers can be converted to their equivalent binary numbers also. So these are the two equivalent binary number columns, and now I'm going to give the chart over here. Okay, so here we are with the charts concerned. So you can see that in the octal number system we have certain numbers starting from the octal number system actually spans from or rather contains digits from 0 up to 7. Okay, so it's basically a base 8 number system. So this can be referred to as a base 8. Okay, base 8 number system. So you can basically see that there are 8 digits in all, so starting from 0 through to 7. Okay, and for each of these digits concerned there is a binary code. So you can see that all the binary codes over here are consisting of 3 bits only. They just consist of 3 bits, whereas in the hexadecimal system you can see that the symbols, or the entire hexadecimal number system spans from that of 0 through to 9, and then we have A, B, C, D, E, and F. Okay, representing the corresponding decimal equivalents of 10, 11, 12, 13, 14, and 15. So it's basically we are having 16 symbols or digits in case of the hexadecimal number system. So that's why this hexadecimal number system is also referred to as a base 16 number system on the other hand. All right, so in this case we can also see that the equivalent binary numbers or the codes corresponding to each of the hexadecimal digits on the other hand are 4-bit in nature. So we have the binary equivalents of each of the hexadecimal digits to be comprised of 4 bits. Okay, starting from 0 and then through to F. Okay, now this is the basic chart about the number systems concerned, and now we need to know how are they useful. Okay, I'll just give you an example over here. So let's say you had a data let me just write down something like this. Let's just come to the octal number system first. So if you had a data, okay, represented in something this way as, let's say, 6, 5, and then this was enclosed within brackets and you had a small 8 below it, then this would basically represent an octal number. Okay, so this is an octal number, and how do we know it? Because of the 8 mentioned over here. Okay, now the corresponding binary equivalent of this octal number would just be, if you just put down the codes concerned. So you'll have, for 6 you have 110, and for 5 you'd have, what do we got here? Okay, 101. Okay, so this is you can take it as the binary equivalent of an octal number. But what happened was that, first of all, the octal number system was of a certain degree of importance, but much more recently, after the processors came in and the computers were there, the octal number system, well, it became a little bit outdated. Okay, and the most important number system, or rather the most widely used number system currently, is the hexadecimal one. Okay, the first processor, or the microprocessor created, was the 4004 by Intel. Okay, back in the late or rather the early 1980s. Okay, this was the first operational microprocessor introduced in the market by Intel, and that this particular chip was basically a 4-bit microprocessor. And now that we have computers today, we know that in computer terminology or digital terminology, well, 4 bits, they make a nibble of data. Okay, and 8 bits basically make a byte. Okay, 1 byte of data. And that all the computers today will work with bytes. Okay, they just work with multiples of bytes, and that's why the hexadecimal number system is most important. You see, whenever we're talking about bits and bytes over here, we know that we have got, well, 8 bits, and that it is equal to 1 byte of data. And now whenever we're talking about storage capacities of pen drives, hard disks and all, we're just talking in bytes. Okay, whether it is KB or MB or GB, whatever it is, it just refers to kilobytes, megabytes and gigabytes. Okay, now they all, if you just look at them in a broader scale, they just all come to the 8 bits. Okay, they just all scale down to 8 bits, so they are just multiples of this particular number that we have over here, or rather more precisely, they are just multiples of 4 bits of data. Okay, that is just referred to as a nibble. Okay, so after the 4004 introduced by Intel, we had the Intel 8080 and then the Intel 8085. So they were all the 8-bit processors that were introduced in the market. And nowadays, the most common types of processors that are being used are 8-bit processors, okay, or we have the 16-bit processors and even 32-bit processors. So you can just see that they are, well, nothing but multiples. Okay, they're just multiples of 4, 8, 16 and 32. So they just are multiples of 4 bits of data, and that is why the hexadecimal number system has become very important, because we can represent it using 4 bits of binary numbers. Okay, now we got the relationship. Okay, now let's just get down to it. So if we just talk about the hexadecimal number system, if we have a number, let's say, just talk about it this way, 7F. Okay, and generally, if you just talk about it in a mathematical term, then this is represented somewhat this way. So this is basically a hexadecimal number. Okay, sorry there, just a spelling mistake. Okay, don't mind at that. So this is basically a hexadecimal number, okay, with base 16. Okay, so here you can just check out the 16. And now if we want to represent any number in terms, any hexadecimal number in terms of binary number or binary codes, then we can do it basically this way. So if you have a binary code of, let's say, 1110 and then 0101, now you can just look up the charts. Okay, now just look up the charts. We have 1110, let's say, where we can, okay, we got 1110 here. That is corresponding to the number E. So this part corresponds to the number E, and the other 4 bits of data, that is 0101, where have we got? Okay, it's here. So that just corresponds to 5. So this represents 5. Okay, now you can see that how it's easy to represent a binary data, okay, in terms of a hexadecimal number. So if you have this particular number, you can just represent it as E just by looking up the charts, and if you have this particular number, you can just represent it as 5. Okay, now let's say since most of the computer systems, they just work with, I mean, most of the processors, they just work with, well, 8 bits of data nowadays. If we'd have an 8-bit data on the other hand, so let's just write it down this way, 1110 and then 0101, and now we're supposed to represent it, this thing, in terms of hexadecimal numbers, then how would we do so? We would just divide it into 4 bits each. Okay, so starting from right, 1 2 3 4, that's one group. So we just refer to it as the lower nibble. Okay, refer to it as the lower nibble, and here the other 4 bits of data, we just refer to it as the higher nibble. Okay, that's interesting. Now the lower nibble, that is 0101, is nothing but equivalent to hexadecimals 5, okay, and 1110 is equivalent to hexadecimal E. So the entire number just comes down to E5. And in terms of processor systems and digital systems, we just write a small h over here, indicating that this number is a hex number or a hexadecimal number. So that was pretty easy. So now you can, given this chart, or rather if you can just remember the sequence, you can just cook up any kind of, or rather, relate to any kind of binary numbers in hexadecimal terminology. So this is how you can represent binary, or rather convert binary numbers into hexadecimal, okay, just by this particular systems whenever we deal with processors. And on the other hand, if you have a hexadecimal number on the other end, you can just represent it using the chart into their equivalent binary number as well. Okay, so now similarly for 16-bit and 32-bit data, you can have, well, a lot many of these numbers. So here for a 16-bit data, let's say we have a data of okay, 2A01. Okay, now this is basically a 16-bit data. Now you can just note the correlation between them, or rather the difference between them. Okay, so whenever we're talking about 8 bits, so it should consist of 8 binary digits. So let's just count the numbers over here in the previous example, that is E5. Okay, we have 1 2 3 4 5 6 7 and 8. So here the entire data consists of 8 bits. So this is basically an 8-bit data. And for an 8-bit data, correspondingly, whenever we just divide it into groups of 4, we get a 2-digit hexadecimal number. So we get a 2-digit hex number. Okay, and whenever we're talking about 16 bits, we should get 4 such groups. Okay, since it should consist of 16 individual binary bits. Okay, now 8 bits consists of 2-digit hex numbers, so it's quite a common sense that 16-bit hex numbers would just, or rather 16-bit binary numbers would just be represented by 4 digit hex numbers. So I'm just gonna relate it over here. So for this number, if we just try and represent it in binary, then for 2 we're gonna get, well, okay, I'm just gonna write it down this way, 2A01. So for 2, the binary code would be, well, 0010. For A, it would be, well, 1010. Let's just check it out over here. For A, yeah, 1010, not a problem. And then for 0, it will be all zeros. Okay, and for 1, 0001. Now if you just write them side by side, then you're gonna get something like this: 0010 and then 1010 and all zeros, and then 0001. So now you can count that, well, we have 4 groups of 4-bit numbers, or 4 nibbles over here, and well, 4 times 4 is a 16. So this is basically a 16-bit number, okay, or a 16-bit binary number, and we are representing it in the hexadecimal number system by a 4-digit, okay, 4-digit hex number. Okay, we're just representing as a 4-digit hex number. So this corresponds to 2A01. So there's our corresponding 16-bit hex number. All right, now if you ask me, well, why do we need to learn all this up? Well, it's because when it comes to, let's just take for example your microprocessor kit in the lab. Over there you're supposed to, well, enter data, okay, by using keyboards. Okay, you use hex keyboards, And now a machine, okay, your microprocessor, okay, doesn't understand anything but zeros and ones, and you have, you know, vast streams of zeros and ones that actually make up your instructions and commands. For every instruction, for example, let's say for MVI command, or more precisely if you just take it as MVIC, for this particular command you have a corresponding hex code. Okay, you have a corresponding hex code of 0E. Now this is actually hex number, which actually stands for in binary as well, 4 zeros, and then for E we have, let's check up the chart, okay, 1110. And then again, if you just use your halt command, then for this particular command you have a code of 76, which in binary actually comes down to 0 111 and then 0 110. So your microprocessor understands the commands by means of all these binary codes, which are, well, long, really long, and we human beings find it very confusing to remember all such sequences. So it's easier for us to understand, or rather more meaningful to represent them in certain codes with which we can just, you know, convert them to the necessary binary codes whenever we require, and easily enter the data into such computer systems, or, you know, microprocessor based systems whenever it's just loading a program or doing whatever. And it also reduces our efforts. Imagine if you had to enter these codes in binary into your kit. You cannot even imagine the number of times you'd have to press a 0 and a 1 button. Oh, your fingers would just pain. That would be painful, really painful. Now, since you're using a hex keyboard, on the other hand, you can just press a particular switch. Let's say you just entered this entire code by using this 0 and by pressing the 0 once and E once. So that just saves your effort of pressing the switches 8 times, since you're entering an 8-bit code. So this is where the hexadecimal number, you know, actually comes in handy. So having said that, we would just like to wind up over here and meet you in the forthcoming tutorial. So till then, it's just gonna be a short goodbye for now, and stay tuned.